Alrighty, this first one up here, how's the water's phase diagram differ?
It has the negative slope.
So the So that solid liquid interface line has a negative slope. So increasing pressure, instead of turning it into a solid, turns it into a liquid. All right, let's put a phase diagram up for water then. So then we've got pressure and temperature, something like that, and solid, liquid, gas, polarization, sensation, I don't remember talking about it, but the significance of the critical point is what?
Of the what? The critical point for water is pretty much just the three
That's the triple point.
of the, okay, no. Oh,
This critical point up here, this one. Once they've reached that temperature, they're moving so fast, it doesn't matter how tightly you squish them together, they still can't be turned back into a liquid. So they're just simply moving too fast. And the triple point, that was where you've got all 6 phase changes happening at the same time. It's literally melting and freezing at the same time, boiling and condensing at the same time, depositing and subliming all at the same time. It has to happen someplace. I mean, they all meet, so it's just an odd thing that happens with everybody's phase diagram, but totally exists. How about this one? Water's most dense, 4 degrees Celsius, and what happens when you raise or lower the temp? How about this one about the swimming pool?
So the pressure that's inside is, I don't know, is greater or less than what's actually in the pool.
So your eardrum gets pushed in because the external pressure is greater than the internal pressure. And since the eardrum is a sensitive membrane, it causes pain. Okay. Magnesium and copper 2 chloride. Okay, so CuCl2 and Mg gets Cu and MgCl2. And AQ, solid, AQ, and since it's copper 2, there's nothing to balance. How do I know that the, how do I know the states? What kind of substance is copper 2 chloride? Whoa, what kind of compound is it? It's a salt or it's an ionic compound. And so if I took a piece of magnesium metal, a chunk of magnesium metal, and dropped it into a container with a bunch of salt, what would happen? Nothing. So to get that thing to react, the only way to do it is to put it into water because it's soluble. So because this won't react if they're both solids, we'll make one of them aqueous. So that copper 2 chloride will show up aqueous because otherwise it won't react. They'll just sit on top of each other and do nothing. Does that make sense? That's how you're supposed to know that that thing is aqueous and not a solid. And since it's a salt, you only have two options anyway, right? It's either a solid or it's aqueous. So this one's aqueous, mixes with the magnesium. What kind of reaction is this? Somebody's trying to say it. Oh, did I say it right there? Oh yeah, I did. It's a single replacement reaction. Excellent. All right. Glad I didn't mess that one up. All right, so I want to know what's going to be left in the container. Doesn't really matter which one I start with, so I'll just go ahead and start with the 43 grams of magnesium. And then for every 1 mole of magnesium, what is it? 24,305. And then for every 1 mole of magnesium, it's 1 mole, and I'll just put copper up here. 1 mole of copper. 63,456. 63,456. Right. So you got 43 divided by 24.305 times 63.5, no, 456. All right. So I got 112 grams of copper. All right, so then I'm going to put 75 grams of CuCl2, CuCl2, 1, and it's 63.456 plus 35.453 times 2, so that's 134.362. And this is 1 CuCl2, 1 Cu, 1 Cu, Cu, 63.456. Okay, so 75 times 63.456 divided by 134, and I got 35 grams of Cu. Okay, so the first railroad track that I started with the magnesium, what's that tell me? Explain what that entire equation is about, that calculation.
It takes 43 grams of magnesium to take out 112.
43 grams of magnesium will make 112 grams of copper if you have enough of the copper 2 chloride. So what's the next calculation saying?
That's 75 grams.
So if I have 75 grams of copper 2 chloride, I can make 35 grams of copper if I have enough magnesium. So which one of these statements is true? The second one, right? Because the moment that I've made 35 grams of copper, what happens? I'm out of copper 2 chloride. I cannot do anything else. So to answer this question right off the bat, I can say that I have this much copper in my container, and I've got 0 grams of CuCl2. Are we okay with that? All right, so what I need to do now is figure out how much of the magnesium got left over, because I definitely have leftover magnesium. So the way we're gonna do that is I'll do it the exact same railroad track I just did a second ago, CUCL2, 134.362, CUCL2, 1 CUCL2, 1 CUCL2, and then I'll go to magnesium. 1 magnesium, magnesium, and 24.305. So 24.305 times 75 divided by 134, and I get 14. I get 14. I get 14 grams of magnesium. So is that what is left in my container, the 14 grams? No, it's not, right? That's how much was used. So I started off with 43 grams. So if I subtract that off, I'm gonna get 19, 20, 29? 29? Yeah. I'll have 29 grams of magnesium, and so that'll be, this stuff will be left over in the container. So 0 grams of copper 2 chloride, 35 grams of copper, 29 grams of magnesium, and how much magnesium chloride is going to be in the container? Well, there was 75 and 43 grams were put into the container, so I have 118 total grams in the container. I'm going to have to subtract off 29 grams and then subtract off 39 grams. So 118 minus 29 minus 35, and I got 54. So that leftover 54 grams of mass must be my copper 2 chloride, or sorry, magnesium. This is my magnesium chloride. Everybody good with that? Okay. And how about this last one?
It evaporates really fast.
It evaporates easily. So when I say something is a compound that is volatile, it'll readily evaporate. So can you give me an example of a compound that readily evaporates? A compound that's volatile? Alcohol? Sure, like rubbing alcohol. So if you've got a spot of rubbing alcohol on the countertop and a spot of water on the countertop, which one of those two things evaporates first? The alcohol. So its vapor pressure is higher, so it's much more volatile. Give me an example of something that's not volatile. Oil's a lot less volatile. How about something even less volatile than that? Yeah, something that's a solid, right? How about table salt? Doesn't really evaporate away, right? Okay. So